Thank you. And welcome, everybody. Good morning. Happy to be here. As mentioned, my name is Jason Bassi. I'm the Director of Sales for Boston Microfabrication. And probably a unique company to be here. We've been experiencing some nice growth within our company. We were founded in 2018-ish, 2019. We commercialized our first products in early 2020 here in North America. And we're focused on micro-precision 3D printing. So from the hardware perspective, I think there's a lot of interesting applications, some that we've already experienced with some of the companies that are within your space. So the first slide here is what we're experiencing is we're seeing a lot of crossover. So people who utilize our technology are often very involved and experts within additive manufacturing, 3D printing, and there may be some in the room now, but also many who don't have a lot of experience in additive manufacturing and 3D printing, right? They're working on parts and fabrication methods within microfabrication, things like injection molding, precision machining, lithography, and they're starting to cross over. And what we do is we give another tool to help with that. So as you know, there's some technical issues going on here, so I'm going to work through it, and I just want you guys to understand that. So the slides may flash back and forth. So within the 3D printing industry, we're experiencing great growth, and we've been experiencing this for years. I've been in the 3D printing industry for 20 years. And when I started, there were a few companies, and there were a few different technologies and a few different processes. And now there's hundreds of companies, many different processes for making parts. And I think everybody's goal really is to work towards end-use part production. So right now within 3D printing, the majority of the growth has started, and it's been within prototyping, research and development. But what we're seeing is more and more end-use applications. And I think it's an ecosystem, right? It's the systems, but it's also the software. It's also the processing and automation and machine learning and things like that. So the real issue that we're trying to address here is parts are becoming smaller and smaller, especially in this consumer electronics market, right? Everybody wants to package and shrink things down, make things more comfortable, smaller units. And traditional manufacturing technologies are very expensive, especially in that early stages, right? To produce a mold for injection molding, for example, on a small complex part could be hundreds of thousands of dollars. Micro machining or Swiss machining or other manufacturing methods can take a long time to set up, get into the queues, breaking into production, things like that. And we're actually producing parts now that can't be manufactured any other way. So, for example, we have within a semiconductor test equipment scenario, we are producing parts that are less than a millimeter cube, feature sizes down to 10, 20 microns, and along those lines. So our vision here is to be the leaders. That's all we focus on in this 3D printing world is micro-precision 3D printing. And what that means is we're focused on the pixel size. So we're DLP technology, vat polymerization, and we're working with pixel sizes that 2 to 10 microns in size. And that means we're holding tolerances of, between 10 and 25 microns depending on the system. And often, sometimes we have to do better than that. So it's a combination. Within 3D printing, I would say, the focus is always tends to be in the past is on materials, is on speed, is on throughput, but it's generally focused on relatively large parts. And some of the drawbacks with current technologies is when you start to get into this precision world is holding those tight tolerances and having the repeatability and consistency within the build. And resolution's one piece of it. So you'll see companies talk about resolution, but really it's the combination of resolution, accuracy, and precision. And that's what leads us towards being able to produce these parts with the tight tolerances, the small features, and be able to look at that towards a manufacturing process, right? So being able to validate a process, verify a process. So it's the combination of those three that are really critical. Here's just an example, and again, not all the examples I show will be within this industry, but this is a good example. It's a glaucoma stent, and you can get an idea of the size of that part. You know, so that helps would drain the eye, help drain the eye for ophthalmology application. But when we start talking about resolution and what's capable with this technology, this is just kind of a breakdown. So the overall part size here is relatively small. You know, 1.35 millimeters by 0.8 by 2.65. But what you start to see are wall thicknesses that are down to about 100 microns, channel sizes of 200 microns. So the question that people will often ask when we're talking about 3D printing is, can you make this part? Can you print this part? And that's the wrong question to ask, right? So if you look at some of the existing technologies, their answer could be yes, we can make this part, right? But how valuable is the part on the right, or the two parts on the right, where it gives you some representation of the part, but none of the critical features are there. The resolution's poor, the quality of the part is poor. You look at our two systems on the left, that's the various 2 micron system and 10 micron system, and you really start to see the benefit of that resolution, accuracy and precision. But even between our 2 micron system and our 10 micron system, you can see a difference, right? I mean, it's 5-fold, right? Although it's high resolution, the tip on the part of the more orangish part is not fully resolved, and there's an internal channel that's probably about 20 microns that couldn't be fully developed. So that's how we look at things. When I have the conversations with our customers, it's really, it's a couple of questions. What's your smallest feature size, right? What's the overall size of the part, and what are the tolerances you're trying to hold? And that kind of dictates what system we look at and what machine makes the most sense. Because in the end, if we can get away with, and this is true with all DLP or a lot of technologies, if you can get away with, you know, lesser tolerances and bigger features, there's probably machines out there that can do it faster and less expensive. And that's the same with us as we work down to a 2 micron system versus a 10 micron system. So you want to go for the system that can produce the part and not overproduce it in a sense, right? So how do people use, and again, there's some people who utilize additive manufacturing or 3D printing quite a bit in this room and some who don't. So what are ways that people are utilizing additive manufacturing and people utilizing our technology? So the obvious is in prototyping, right? It's getting parts in hand quickly. And especially as you're developing, there's a lot of newer companies here, people trying to get technology to market, trying to demonstrate their technology. And when you're trying to build those initial units or you're iterating quickly, being able to get these parts, especially this type of part, these are hard, right? I mean, the lead times just for samples could be 8 weeks with traditional manufacturing or something along those lines. So there's a lot of value of being able to produce these parts and produce them quickly. The other place we see a lot of interest, and it's been somewhat of a surprise to us, is in this manufacturing jigs and fixtures. So as people are working with highly precise parts and small parts, they need to be able to handle those. So they need to be able to create fixtures for the parts, different assembly aids, end-of-arm tooling, things along those lines. And then there's the actual tools. Now, this can be a little misleading, right? So for those in the injection molding world, the real gold standard would be able to 3D print molds that can produce hundreds of thousands or millions of parts in the materials that you want to use. That's not quite the case. What we see is you can potentially print inserts using our high temperature materials, and you might be able to mold 10, 20, 50, 100 parts in the materials that your end materials that you're looking for. But even so, there's things like casting, making patterns, silicone molds, things along those lines where we see a lot of use within our using our technology. And then lastly, what the real goal, what we're all working towards in this industry is being able to use our technology for end-use parts. And there's a number of different factors which you have to look at, right? One is, can you produce the part and meet the specifications? That's the first thing. And we do that, what we call as a benchmarking process. We generally do that for free. You send us a file, we make your part, we review your part, you get the file. Does it meet the specifications that you have? At the same time, we're looking at the business case, right? It really, in the end, it comes down to dollars and cents. What are the volumes you're making? Is this technology right for that? And then usually the last few things are, do we have the right materials, right? Because within the 3D printing world, you don't have the range of materials that you might have, let's say, from an injection molding standpoint or other processes. So, and then we look at process. So what do we see? So we're not experts. This is our first time being at this show in the AR, VR world. What we do know is we have a number of large customers who are using our technology. And they use it in a variety of different ways. But I think as I break it down, what does it seem like? Where is the best use case? It's kind of in these packaging, enclosures, housings. We do a lot on the connector side, electrical connector side. But as, let's say, cameras or microphones or optical systems are getting smaller and smaller, again, how do you hold all that together? Where do you get those components? What's the best way to do that? And even things like now we're seeing, and I saw like the haptic hand out in one of the booths, you start talking about fluidics and moving liquids and air around, and for some of the hardware, you know, we see a lot of applications along that line. So it's just so what are we capable of doing? Just a couple quick examples. One thing I like to show is within 3D printing and even within traditional manufacturing, making a pattern of holes, highly precise holes, is very difficult and costly. And here you see, you see 1,500 holes that are a couple hundred microns, spaced 50 microns apart. There's no other 3D printing. I never like to say there's no other 3D printing technology because there's always something else that exists. But this is very hard to do from a 3D printing perspective and a traditional manufacturing perspective, and to hold those tolerances where that doesn't become just a blob and holes that are all filled in. And again here, a fiber optics example. But what's interesting about this is now you start to get into something that's a little more custom, like trapezoidal through holes, right? And they have a shelf within there where the end clicks into and snaps into that. So that's what 3D printing gives you the freedom to do. So it's one thing to drill a hole, it's another thing to do a complex shape, and then it's another thing to do it over and over again at a small scale and hold those tolerances. Again, on the connector side, what makes electrical connectors interesting is that the tolerances in the stack-up tolerances are very tight on these parts. And again, within that world, the parts aren't necessarily tiny. We make some pretty large parts, but it's holding that positional tolerance throughout the whole part. And again, these tools can be extremely expensive. And then something here that might resonate a little bit more with the group. This is for a surgical application, an endoscope shell. But this is what I'm talking about in terms of within this part, there's a lot of things happening. There's water lines, there's optical lines, there's light, there's guide wires, and the tolerances on something like that might be plus 15 microns minus 0, right? So again, you know, traditional manufacturing, that's kind of, you know, there's some technologies out there, but to make that is not easy, and it's costly, and it's time consuming, and to do that from a 3D printing perspective was nearly impossible until we came along. So just a few examples. And so what does this mean towards looking at production? And again, I talked a little bit about this early on, but what we like to see is I guess kind of the smaller and more complex the part is, the better the chance our technology can be used towards end-use production. And I'm talking, you know, tens of thousands, hundreds of thousands of parts. Getting into the millions is still pushing it, but there's some examples where it could make sense. So a relatively simple part, it doesn't make a lot of sense, right? You can go cut steel and make a tool and produce that relatively inexpensively and relatively quickly. But as the part becomes more complex, that's where it makes a lot of sense. A lot of the parts we're working with, some of these tools from a production perspective are hundreds of thousands of dollars, and lead times can be 18, 20, 22 weeks. And then there's the chance that they don't get it right the first time and they go in there and they modify and tweak the tools. So that's kind of what we're looking for. If it's a large part for our system, the scenario for that to be usable in production beyond 10, 20, or 30 parts is probably doesn't make a lot of sense. And what's interesting is with traditional even now compare it to traditional 3D printing, the cost of materials generally within the 3D printing realm versus traditional manufacturing are generally higher. They're processed materials. They might come in powders. They come in liquids. They come in spools. And the crossover for traditional parts that are larger is a lot lower, right? That crossover from when I'm going to move to a tool versus to when I'm going to continue to 3D print, because the cost of those materials adds up very quickly. For us, materials is very low, right? So because the parts are so tiny, that offset of what you might see from your cost of materials, you know, from injection molding versus 3D printing is very little. So you see that where it can make sense longer with higher volumes. So the real key here is that we're not investing in tooling. That's the big takeaway. So that's really your break point. Now, once you invest in a tool, your part price is going to be lower than our part price. So that's where you look at the math and the crossover, right? Here's an example of a part. We have it in our booth, and we do have a booth here. It's 319, and you can see a number of different applications we have. But I think that part would have a number of guide wires going through that. You know, we could print with one machine, let's say 10,000 of these per month, and the cost would be 38 cents, right? So that's a good example. You get parts smaller than that, obviously you can fit a lot more, and the cost can go down. So how does just real briefly, how our technology, what is our technology? We call it projection microstereolithography. So this was hence the name Boston Microfabrication. It was developed by MIT professor Nick Fang. And we utilize traditional DLP, so standard DLP light engine. But what we do is we use precision optics, motion control, and software to really control that down to the pixel size. So for us, it's all about having control over those pixels. So the standard pixel size in a DLP light engine is 7.6 microns. So on our 2-micron machine, we're actually reducing that. On our 10-micron machine, we're slightly enlarging that. And then we do have a 25-micron machine where we enlarge it more. Other DLP technologies on the market are actually expanding that quite a bit. So if you see larger build volume, your build volume is kind of inherent to the size of the pixel, to the resolution. So you see larger machines that can build bigger parts, they're giving up resolution, right? So we're maintaining that. The other thing that we do that is patented is we take something from the semiconductor industry and we actually do stitching. So we have a relatively small exposure zone, so that flash, but we can do that multiple times within a layer, right? So we can do either a lot of parts and maintain that precision and accuracy throughout the build, or we can do larger parts. And that's how we don't sacrifice that, again, going back to those tolerances, that accuracy and precision throughout a larger build. So in a nutshell, that's kind of how our technology works. Again, it's a vat of resin. We call it vat polymerization. We use standard acrylate-based resins. We also have ceramics. They're thermoset materials that are photo-cured. It's an open material system, so we offer our own materials, but you can also use proprietary materials. You can use third-party materials. Now, it's not always as easy as taking something off the shelf and porting it onto our machine. But in general, that's an overview of our company, kind of how we see where we fit in. And I would be extremely interested to hear from more of the people on the hardware side within the conference where they think the technology fits in well with some of the work that's being done. So that's my presentation for today. Thank you. Sure.
We are going to open up our remaining time in the session to any Q&A. If you have any questions for Jason, please feel free to step forward to the microphone. Thank you.
Hey, Jason. Thanks for your time. Great presentation there.
Thank you.
Could you please share with us your experience in multi-material printing in that scale? Have you guys worked with like printing of piezoelectric materials and the development of those type of actuators?
Yeah. So the multi-material 3D printing tends to be a little bit easier on the jetting side. So you'll see some systems out there that use multi-materials, and generally they're jetting the materials so they can have multiple heads to do that. You know, pros and cons with that, of course. For us, because we use a vata material, it's possible. We have experimented and played around with it, but then it becomes limited layer to layer, right? You can do a layer in one material and you can do a layer in another material. It's probably not high on our radar in terms of our product roadmap. So for our technology, for this type of technology.
In and out.
Thank you.
The door kind of slams when it shuts. Yeah.
Hey.
Hi, how's it going?
Good, how are you?
So pardon my ignorance on resin 3D printing.
Sure.
I'm used to traditional, like PLA, PETG.
Yep.
And so I was going to ask a question about support structures.
Sure.
Are there similar problems with resin printing, and
Yeah.
what kind of challenges, what things can't you print?
Sure, that's a great question. So within our technology, so supports are generally, so parts are overhangs and undercuts and things like that generally need to be supported one way or another, right? Because it's an additive process. So in powder systems, the powder will do that. In systems like you're talking extrusion-based, there's physical supports. Same with DLP. Now for us, we're a top-down system, so we don't require that on every part. Bottom-up systems require it on every part. Again, the viscosity of the resin can support a lot of these overhangs, but there are situations where you do need supports. And generally, our supports are tiny. They're cone-shaped. There may be a 200 micron base, 50 micron tip. And the software adds those automatically, or you can generate those. But there are situations where you do need supports.
Great,
and they're
thanks.
very easy to remove. Yep.
Great, thanks very much.
Thank you. Yep.
Hi, Jason.
Hi.
Thank you for the lovely presentation.
Sure.
I had a question about the materials in use right now at
Yes.
BMF, and I did not happen to see any clear materials in the presentation here, and
Yep.
I was wondering if similar resolutions can be achieved on clear materials, especially for diffractive optical elements.
Yeah, so translucent material is possible, but optically clear on our system is not. So even colorless is not. And there's not to say that we're looking at it and we're working, there's some material limitations. So we use 405 nanometer light source, which is one of the limitations. And also we print at very fine layers. So we print down to 5 to 10 to 20 microns. So with a DLP light system, you're UV curing the part, you have to control, because we print at such fine layers, you have to control the depth of penetration. And with that, you're using light absorbers, which are tinted. There are some clear light absorbers. There's some ways to work around that. We're working on that, but currently translucent. You'll see the yellow translucent. They're clear parts. You can see through them, but we don't get into optics or optically clear or even water clear right now.
Thank you for the clarification.
Yep.
Just a follow-up question on that, if I may. Speaking of the material classes in use right now, do you believe there is an industry-wide preference over the kind of chemistry that goes into the resolution, such as an acrylate chemistry or the thiolene chemistry or something?
Is there a preference within our system or within
for microprojection lithography in general, for resolution, is there a certain chemistry? Because
I think resolution. I think we get into some filled materials. That adds some challenges with light diffraction. I think higher viscosity materials can add some challenges maintaining. So lower viscosity materials, generally, we can get the best resolution and accuracy within the parts. Chemistry-wise, I'm not sure if there's a big preference. I think it's more about just capability of the materials with the curing system that we have.
Thank you so much.
You're welcome.
I think we have time for one more question, if anybody has one.
Could you speak to what's needed in terms of a washing system?
Yep. Sure. So because the parts come out of the resin, there's generally excess resin on the parts. So we wash with an IPA solution, and we actually use some very off-the-shelf systems. There's something from Form Labs called the Form Wash. It's a $800 system. It circulates the IPA and rinses the part. And then there's a quick post-cure, and we also use a Form Labs product for that. And generally, that's a 3-minute UV post-cure at 45 degrees C. Yep.
Jason.
Okay, thanks everybody for your attention.